subject at hand is quantum mechanics. This occupies a space in the collective conscience of just really hard physics, with grueling mathematics and very difficult to understand. That has some merit, somewhat fair. It's certainly not easy to do calculations, but it's also a very successful theory of physics that accurately describes the way things are. So, for that reason, anyone thinking that they're getting an education in physics should probably take the time to get some conceptual familiarity with what's going on there. But more than that, the other thing it is a really hot, vibrant time in history of like rapid change, and it's also accurate to call quantum mechanics a bona fide revolution in science, one of the biggest it's ever had. So, to me, it's also fun. So, I invite you to see it all of these ways if you haven't yet. The story of quantum mechanics picks up in earnest with this idea of the ultraviolet catastrophe. And it's basically this. Rayleigh genes, using laws of classical physics at the time, they set about to understand and explain what it should look like if this thing called a black body, like a perfect emitter of light, it's just something that gets really, really hot. It's this idealized hypothetical object made of metal. It's going to try to reach thermal equilibrium with its surroundings by emitting light. The dotted curve, the Rayleigh-Jeans curve, is kind of saying that as the black body gets hot, it's going to reach thermal equilibrium through a mechanism in which it kind of makes infinite amount of infinite frequency light. So if you look at this wavelength along the horizontal axis, wavelength is inversely proportional to frequency. So moving to the right on this is high wavelength, low frequency. Moving to the left is low wavelength, high frequency. So approaching this vertical axis, you're talking about infinite frequency light, which is like infinitely energetic light. And everybody at the time knew that this was a huge problem for the field. No, it's just nonsense. Like, that's not what happens. Furthermore, the experiment was actually carried out. These are the observational curves. So as black bodies get warmer, 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 temperatures of 2,000 Kelvin, 3,000, 4,000, 5,000 Kelvin, none of the observations, like, they match the Rayleigh-Jeans kind of curve for a bit, but then after a peak in the visible range for this one, it falls off super rapidly, and then as an observation, this just makes a lot more sense because you're back down to zero radiation intensity by the time you're approaching these like infinitely energetic kinds of light. Super energetic kind of light, less energetic light as you move to the right. The other thing you notice on this set of curves is that as you warm up a black body, its peak radiation, the color of light it will emit as it heats up is getting more and more into the visible range. And then a hotter object will appear more yellow, more blue, and so on. When you're up at this peak, it's going to appear yellow, but notice you are making a bunch of red and a bunch of blue, so these are going to add and appear white. But again, just to drive it home, nowhere in these observation curves are you having anything like the predicted outcome for the theory of classical physics. The ultraviolet catastrophe, however, was not the only issue physicists had on their hands in the late 19th century. Also around this time, it had been pretty widely known that incident light on a metal surface can make electrons pop off the surface. Um, this is demonstrated by charging an electroscope and shining light of a certain frequency on it, and you see it discharge the electroscope. But the conundrum was that if you shined red light on such a setup, or on this setup pictured here, this is meant to be a circuit, if you could shine a certain kind of light on this metal plate, or on a charged electroscope, not pictured, you can give them a nudge, and they will make it all cross and complete the circuit, and you'll show current flowing in here. So the problem with the photoelectric effect, though, was that if you shined red light on this thing, you wouldn't get a current, no matter how bright your red light was. However, if you shined violet light on the thing, you would get a current. No, even if it was a very dim light, you would get a little bit of current. So that's weird, because you could have all this red light flooding the plate that in total would mean a lot of energy, right? But meanwhile, you could, on the flip side, have a little bit of blue light or purple light that would be like, in its sum total, a lot less energy, and yet it is capable of doing what the large amount of red light cannot do. So that's a problem. And prior to Max Planck's theoretical breakthrough, no one could figure out why this was. Okay, but why, right? Like, this is what Max Planck was obsessed with. Like, he wants to understand black body radiation. It's like ruining his life that he can't figure it out. He's working on it for like, I don't know, 5-6 years. And he just is trying every theoretical approach like possible. Finally, in what he calls, like a direct quote of his, it was like in an act of desperation, he just has this crazy, wacky idea. I don't know. It's like I'm trying to help you appreciate how weird it was that he would put forth, posit this notion of like how matter really was. But like, there's no reason to think that atoms were not just really tiny versions of the objects we see every day that Newtonian mechanics explains really well. There was no reason at the time to think anything but the classical laws of physics, the Newtonian mechanics laws, should somehow explain this. So if you're going to explain black body radiation and figure out why, like get around the ultraviolet catastrophe, this like nonsense prediction that's really, really egregiously mismatched from observed reality, you're going to have to account for how it is that the bits of matter that make up the black body radiator are converting their energy into light waves. So Planck is like, okay, I've tried everything. I'm just gonna do this wacky thing and say matter doesn't behave classically like we're assuming it does. Instead of continuously integrating over the curve of all possible energies that the emitted light could have, instead you could like say that only discrete amounts of energy could escape from the black body at one time. Like the walls of the cavity could only make discrete energy packs of light. only specific amounts of energy could be converted into light in any given instant. And then, if you say that, then I can't fully explain the math, but it's a Taylor series instead of a continuous integration under the whole curve. And then it's like a geometric sum, and voila, he predicts, using that math, using that theory, he predicts curves that are super close to the observed black body curves. And then a few years later, somebody totally confirms the prediction. So these specific packs of energy, like this is the big deal. This is the coup d'etat. He's just, for no reason at all, saying light only gets off of this thing in discrete amounts. I don't know. How do you wrap your head around this? I'm racking my brain trying to come up with like an analogy that would help you kind of get your head around what quantum means, why it's the thing that gets you out of the ultraviolet catastrophe. And I don't know. I think I came up with something. It's kind of simple. But imagine you have like a kiddie pool that's completely full of water, and you want to get all the water out. This is analogous to a black body trying to offload all its energy to its surroundings. Like it's a hot thing trying to reach thermal equilibrium with its surroundings. You've got a black body full of energy, and you got a kiddie pool full of water, right? And Planck saying the light could only escape in set amounts, discrete amounts, is kind of like saying, well, I'm going to bail out my kiddie pool with a mug. And just as crazy as Planck's idea of a quanta, like the rule is you can only use your mug, or like maybe a slightly bigger mug, and then maybe a pint glass, something like that. Maybe you have like 7 different sizes of vessels you could use to get the water out of the kiddie pool. But the weird part is you're only allowed to bail out the kiddie pool via completely perfectly full, topped off mugs of water, pint glasses of water. And what that would mean is no single event of getting the water out of the pool would be like those you couldn't just walk up to the pool and flip it over and get all the energy out at once. You couldn't just have infinitely many super big amounts. You couldn't have a small amount of big energy loss events, to like mix the metaphor. You could bail out many times, like that's what you're going to have to do. And some of your sizes of cups could be used more often than others, but you can't just go invent a huge bucket to just get it all out in one go. But the quantum theory explains this conundrum too. So if you recall, if you're shining light on a metal plate, and it's not the intensity of the light necessarily, but it's the color of the light that makes this thing go. Planck's idea of the quanta explains this too, and it took Einstein to bring the two ideas together and published on it, and this is what he won the Nobel Prize for, one of the things. And how it works is this. If you recall, shining red light on this plate, no matter how many times you shine a red light wave on it, it's never going to make it go. But if you've got a quantum theory of light, in other words, if light is just behaving like a particle, it's coming in discrete packets, and it interacts with the electron in the metal surface here, then if only a single photon of light can interact with a single electron, if red light's not enough energy to get you across, then it's never going to be, no matter how many times you try. However, if violet light is enough energy to nudge you across, it's that single energy transfer you need. If a single photon is carrying that much energy, violet, and it passes it to a single electron, that single electron is going to get across. So this explains very well why red light in any amount will not make it work, but violet light in very low amounts will. So here we are. We've got light is both a wave and a particle. Wave-particle duality. Not many people are happy about this situation. It gets worse or it gets better, depending on your perspective. The other thing we can do is take a device that can shoot electrons toward a crystal, like a solid crystal structure. And since it was then pretty newly known that a solid crystal is pretty much a bunch of empty space with some highly concentrated positive massive spots called the nucleus, right? So if a crystal lattice is like a bunch of these nuclei with like a hazy negative region around them, but this is where all the mass and positive charge are. If you give a high speed negative charge thing, it'll pass right through this thing, right? If it has enough energy, it's just going to make it on through. And lo and behold, what happens, you see like a wave pattern here in this drawing. The simple version, the explanation is, what you see is slit interference. You see a beam of electrons hitting this wall exactly like light would if it were passing through a diffraction grating. That's pretty funky. And we can really do these things. The Penn Physics Lab have a machine that does just this. If that cathode ray, or those electrons, are going through a crystal lattice like that, and they are striking a phosphorescent coated plate, they will make regions on that phosphorescent plate glow. So what you see as bright spots here is the places where the electron beam is hitting the plate, like the backdrop behind it. And the reason it's dots in a two-dimensional field is like, you're not actually doing a double slit experiment, which is just like showing you the relative densities of waves arriving there in a linear fashion. It's not a linear report. You have to imagine, like, if you took that double slit and you rotated it so that it was many, many double slits, and the waves had to pass through each of them in succession. That's what it means to pass through a crystal lattice. So basically, I'm here to tell you this is proof that electrons are waves. Weird. So de Broglie runs with this idea of electrons as waves. He's like, well, I mean, that means that matter is waves. Like, matter is waves. And, he doesn't just sit there and decide that he doesn't proclaim it to be so. He does the theory work. And he comes up with this equation. He derives that for all mass, m, its wavelength is dependent on the mass and its velocity. But wavelength is also directly proportional to Planck's constant h. So this is all given here. And before you get too worried, it works out that for stuff like your wavelength is 10 to the negative 36. This is like this is a nothing number. This does not matter in your life. But for electrons, it matters. Like, the reason you get that diffraction grating interference pattern is that the wavelength of an electron with velocity is on the order of the size of atoms. Once Planck theorizes quantum theory, and it has these big successes in explaining photoelectric effect and blackbody radiation. The, then the first couple of decades of the 20th century ensue, and they were a grand revision of physics. There was nothing less than a new atomic model. So what we're looking at here are, are the energy states that an electron can exist in. It's difficult to overstate how radical this idea was, and it had far-reaching implications. Basically, what the diagram is telling you is an electron can exist in a ground state and be excited and excited further and further yet. But if you supply, for this atom, I don't know what this atom is, if you supply the 122.4 electron volts to something in the ground state, you will rip that electron off of that atom and ionize the atom. You cannot be in between. You cannot be in between these levels. It's like trying to stand between the rungs of a ladder. One of the most famous kind of concepts to come out of quantum mechanics is the idea of Schrodinger's cat. And if you haven't heard it before, it's this notion that, say you've got a cat in a box, and there's this radioactive decaying element in here, and it may or may not, it has a 50-50 chance of like causing something to drop this hammer on this vessel of cyanide, and then the cat's dead. And Schrodinger like employed this thought illustration as a way of conveying, in a letter to Einstein actually, like how it is a conveyance of like how weird quantum mechanics is, but it drives it home because it illustrates, it points out like the non-example, like a cat in a box with poison just isn't like this. Like, I am either here on this chair or on that other chair. I am not on both chairs, or neither. But the point being that quantum mechanics is that freaky. It is that the cat is both alive and dead simultaneously until you open the box and look and see. It is not that you just got it wrong. It is that neither state existed alone. Both states existed simultaneously. But Schrodinger did more than that. He's credited with wave mechanics, which is like also known as the Copenhagen interpretation, meaning that the just single sentence wrap up of that is an electron has no definite position. So like any model of an atom that shows you a very nice, neat kind of curve drawn around a nucleus, that's not the full picture. The full picture is something more like this. There's a probability cloud, and the Copenhagen interpretation, or Schrodinger's wave mechanics, dictate that the electron is in all of these places. These are just the probabilities of finding it somewhere. And then you need to like connect up that kind of unsatisfying situation with this explanation Heisenberg gives. It's also famous, his uncertainty principle. And what he's saying is that you can know where an electron is, or like an atomic sized quantum thing, or you can know something about its momentum, but you can't know both. So the uncertainty around position as a product of the uncertainty around momentum is at least Planck's constant over 2 pi. And the reason for this is that if you incident a photon on a particle here, it scatters, and you can detect that. But there's going to be then a recoil to that electron. You will have fundamentally changed the state of the thing. like that experiment you did for two-dimensional momentum, the collision with the two metal balls, that it is not at all how you can think about photons and electrons colliding with each other. You never get to know all of the before and after information for everything involved in the collision. And this is just deeply unsettling to the community. So let's review. There's this problem that quantum mechanics has to come in and solve, but by doing so has all these other implications, all these other outcomes. And physicists of the late 19th century there was a lot to take in. They had to accept a lot of new ideas. And this is a broad list of them. So I say, question, is light a particle or a wave? Answer, yes. Question, is an electron a particle or a wave? Answer, yes. And then there's this uncertainty principle from Heisenberg, which states that the more you know about the position of something, the less you can know, the less you can know, the less that it is possible to know about its momentum and vice versa. This is not a reflection of how good your instruments are. That's like a critical point. An electron has no definite state until you measure it, at which point it retroactively was in that state all along. Electrons do not have a position until you measure them. Yeah. Feynman, one of the most famous physicists and also physics teachers, in the 60s and I think maybe 50s, he was out there giving this public talk. And this is like repeated in the famous Feynman lectures on physics, which was like for not exactly a lay audience, but an undergrad audience that wasn't maybe physics majors totally. And to his mind, what you needed to know, the thing that would encapsulate all of the quantum weirdness is like this thought experiment he has, which is based on real experiment, but he kind of like puts it together in this talk. And there's experimental data you can cite to show all of this is right. Like he's not just making it up. It's not a thought experiment in the way that Schrodinger's cat is. That's more just like a paradox, a mind puzzle to illustrate a point. Feynman is trying to illustrate a point, but it's real points based in physical reality. So he starts it like this. He's like, let's say we're going to spray these like particles, these lumps, we're going to call them bullets, at these two openings in a wall. Some are going to pass through uninhibited, and some are going to ricochet off. There'll be all these ricochets happening. And then you want to see what ends up hitting the backstop behind it back here. And you've got this movable detector, and say that's like a bucket. So you're going to fire a particle from here. It's going to go through one of the openings, and it's going to end up in the backstop. And what you're going to do is you're going to move the detector. You're going to move your bucket back and forth along this called the x-axis. And then you're just going to leave it somewhere for some time. And you're going to let your bucket fill with all the bullets that it's going to get filled with. Then you're going to move it down the line and let some more time pass. And then as you go all the way up and down this, you'll be able to get like a probability profile for how often the lumps of stuff, the bullets, hit different places on the backstop. So, particles through two holes, how are they ending up in the backstop? That's the question. Here's how they're ending up in the backstop. You're this likely to hit this area in the backstop, probably because you went through hole 1. Yeah, P1 corresponds to hole 1. And then you've got the same symmetrical profile for hole 2. You add them together. Interestingly, on the exact opposite side of this like blockage, no hole here, but this is where most of them end up. If you've got both holes open for sufficiently long enough time. This is where all the lumps of stuff are going to get, the particles. Now, he says part 2 of this thought illustration is to say, okay, if instead of shooting lumps of stuff, we were making waves. This is an overhead view of maybe a water wave. It's going to hit a wall with 2 openings in it, same as the first setup. What comes through here, then you get these overlapping patterns of concentric circles of wave disturbances emanating in phase with each other in time from the 2 openings. Then you have a similar detector, and you're going to say, okay, here, what's the amplitude of the combined waves here? What's the amplitude of the combined waves here? What's the amplitude of the combined waves here? You're going to add the intensities together, and you're going to get the familiar double slit pattern. So then the idea goes, once we've established what particles do when they go through the 2 holes, and we've established what waves do when they go through the 2 holes, let's see what electrons are. Let's rerun the experiment by shooting electrons at the 2 holes. This is a capability the scientists of the day had. They're going to shoot electrons at the 2 holes, and then run the detector up and down the backstop, the same as with the previous 2 iterations. Now let's just take a listen at what it's like when an electron hits a detector like this. So that's what it sounds like. It's worth hearing because what you hear is that the clicks are separated in time. So even if it seems like 2 are arriving at the same time to your ears, it's really just your inability with your bare senses to separate those 2 events in time. So what that's illustrating, the clicking sound, is that electrons arrive one at a time, which is notable in this experiment. So let's peel back the curtain. What pattern do we get? Not what a lot of people might have expected, especially at the turn of the last century. So we're pretty convinced that an electron is a particle, a nugget of stuff whizzing around in an atom. It's just really spooky and weird that these things would interfere with each other. I mean, they're matter, right? They're conceived of as particles with mass, and so they should be behaving like marbles. And yet, in this experiment, they most certainly are not. This is data of that very experiment from 2013. Pretty definitive double slit patterns. It's kind of astonishing. And then Feynman continues, and he says, well, so Schrodinger has this idea that electrons exist in all states until observed. And Heisenberg has this idea of the uncertainty principle. You can either know its position or momentum, but not both. Or more accurately, the more you know about position, the less you know about momentum. So he devises this iteration in the series of trials here, where he's like, okay, we're going to have a light source. So he's, in his words, well, maybe people's rebuttal is that electrons are doing something weird. They're going through both, or one, or doing a circle around both. I don't know. Whatever might be happening, it behooves you to try and check which hole the electrons are going through, to try and understand this weirdness. Okay, so you do that, but to see something, to detect the presence of something, you need to shine some light on it. So you get a light source that will you'll be able to sense a disturbance in the brightness in this area if the particle goes through that hole, that zone. And what happens when you do that if the double slit pattern for an electron didn't freak you out, then I think maybe this might. The act of checking to see whether an electron went through a hole or not makes the pattern turn out like particles. The wave interference pattern that electrons display, that we didn't think they were supposed to, goes away if you shine a light on it.
This ball has end. This ball not has end. So this toy can be here or here. And then this toy cannot be here. So this toy can be here or here. Then this toy cannot be here. This toy can be here. And this toy cannot be here. This last time, this turn can be here or here, and this turn is not be here. This turn can be here or here. The turn is not be here. The turn can be here or here. The turn cannot be here. And that you can be here and then that turn is here. That's pretty. We don't have anymore.
Is that it?
Yeah.
Thank you. Did you get all that? Well, she's only 2. We're still working on it. I'll read it to you. Quantum Physics for Babies. This is a ball. This ball has energy. This is a ball. This ball has no energy. All balls are made of atoms. There are neutrons, the purple ones, and protons, and electrons, the green ones flying around on the outside. An electron can be here or here or here. But an electron cannot be here. Or here. All electrons have energy. This electron has the most energy. This electron has the least energy relative to the other 2. There are no electrons with 0 energy. This energy is quantized. An electron can take energy to jump up. And it must give energy to fall down. This amount of energy is a quantum. You're now a quantum physicist. Aren't you glad you went to Penn for the summer?